So chapter 8 brings us to exponential growth and decay, and we'll do some comparisons between exponential growth to linear growth. So our first example, to kick off, we're talking about two different types of investments. $1,000 principal or initial investment. We have two different plans. Plan A says that at the end of each year, we'll earn 10% of our original investment, which would be $100, added into the account. So each year, first, second, third, and so on into the future, we'll earn exactly $100 added to the account every year. That sounds a bit like a simple interest problem, but we'll see that in a moment. Plan B says that at the end of each year, we'll get 5% of the account balance added to the account. And I think we'll recognize that as compound interest, given that 5% of the account balance is added to the account. So that's relative to what's in the balance, or what's in the account at the time. So let's see. For the first situation, let's name a few variables. Y will be equal to the balance of the account at any given time, and X will be equal to time in years. Okay, so then it's pretty easy to see what the situation is for this account. And I'm using y and x because this turns out to be a linear model. Y equals mx plus b is what we'll see. So we know that for any given year, the account balance y is equal to the $1,000 that we started with plus the $100 times x for each year that this account is in existence. So it's going to be paid $100 the first year when x equals 1. By the end of the second year, x is 2, so it'll earn $200, $300, $400, all added to that base of $1,000 going into the future. So this is a nice way to model scenario A. And let's do the same thing for scenario B. At the end of each year, we get 5% of the account balance added to the account. Well, since we recognize that as compound interest, we can just use the compound interest formula. So our future amount is the principal, which is $1,000, times 1 plus the rate, and the rate is 0.05 as a decimal, to the power of t, compounded each year money's earned on this account. And maybe simplifying this a little bit, just adding 1 and 0.05, we can write it in this form. Okay, so this is a linear scenario. Each year we add exactly $100. This is an exponential scenario. We'll learn how to recognize these later on. One key thing is to see that there's a t in the exponent. One of our variables is in an exponent. So that's how we recognize possibly that this is an exponential situation, whereas there aren't any exponents here. This is times x. That's our linear scenario. Anyway, let's compare these two plans. So what's the better deal for a 10-year investment term? So you might instinctively say the compound interest scenario, part B, is going to pay more than part A, but that's going to be relative to time. So let's check out our 10-year situation. Well, what we've got in both part A and part B that we've set up right here, this and this, are two different models for each of these scenarios. In other words, we have a way of predicting what the account balance is going to be based on the number of years that's gone by. So for part A, Y, the account balance 10 years into the future, is equal to 1,000, and we just substitute 10 for x, 100 times 10. We're 10 years into the future, and that's 1,000 plus 1,000 is $2,000. Put a dollar sign, take it to the nearest cent, and let's see, for part A, well, A is 1,000, and this is 10 years into the future again. We could use the same notation I just used for the first part. A, 10 years into the future, is 1,000. We just set t equal to 10 times 1.05 to the power of 10. Plugging this into a calculator, being careful that 10 is actually in the exponent, maybe even using parentheses if we're worried, we'll get that this is approximately equal to $1,628.89, rounding to the nearest cent. Okay, so which one's better in a 10-year plan? Well, it's like part A. There's more money here, right? So this is a better investment for a 10-year plan. So, but that might contradict what our initial feeling might have been, which was for 40 years, or for the exponential versus linear, we'd think that the exponential plan would pay off better. Well, it just needs time to do so. So let's see the 40-year plan. So it's A and B. So now for part A, again it's y of 40. So the balance 40 years into the future is 1,000 plus 1,000, or 100 times 40. This comes out to $5,000. Okay, plugging things into part B's model, 40 years into the future, 1,000 times 1.05 to the 40th, 40 years into the future, and that's going to give us approximately $7,000, $7,039.99. So sure, maybe the exponential model is not better at first, but eventually it catches up and surpasses the linear model. In other words, the value is more. So depending on the length of your investment, the linear model could be better than the exponential, but the longer you go, the better off the exponential model is going to be. So the last question here is, what length of time does the second investment scenario catch up to the first in terms of payoff? Well, there's not really an easy way to do this, at least not a technical, straightforward way to do it other than guess and check, and that's all I'm going to suggest for this. What we're really looking for is, when is y equal to a? So in other words, when is 1,000 plus 100, and instead of t or x, I'm going to use t. They're both time in years, so we can mix those up. They're the same unit, so we can just use the variable in both places. 1,000 plus 100t is equal to 1,000 times 1.05 to the power of t, and guess and check. Right, that's the best thing we can do. So we guess a value for t, and then we check it to see whether or not, or how close to being equal these two values right here are. Okay, so maybe a hint is that if we look above, part A here was more than part B, and then we moved to 40 years, part A was less than part B. So somewhere they crossed each other. In other words, these values were close together, as one went from being larger than the other to being smaller than the other. So we know then that it's between 10 and 40, which is a pretty large gap, but you can start to narrow it down by guessing and checking. Once you've done a few rounds of guessing and checking, you should get to the approximation that t is about 26.6 years, if you cared to work out the details of that one. I won't do it because it's just a little bit tedious and not worth having in a video. So plus it's not really a main part of this section's problems. So let's move on and look at the difference between absolute or linear growth and exponential growth. And what we saw before is that compound interest is an example of exponential growth. The account that has money added into it based on its current amount, current balance, that's a relative change of 5% that was added to it each time. So that relative change was always the same. So when relative change is constant, that 5% that we saw, then we have exponential growth. Okay. On the other hand, the other account just had $100 added to it each time. That was an absolute change. $100 plus $100 each year is an absolute change in the balance of $100. So that's a linear growth scenario. So that kind of confirms what we were calling each of those scenarios in the previous example. Now, this is the question essentially right here in front of us that we just answered. At the end of each year, you get 10% of your original investment, $100, added into the account. So I'll just write it out. The absolute change is equal to $100, and that's each year. So from year to year, that doesn't change. So the absolute change is constant. This is linear growth. Linear growth. Okay, and then part B, we'll recognize again, at the end of each year, 5% of the account balance is added to the account. That's relative to the balance. The amount that's changing is relative to the balance, but it's always 5%. So we know that this is a constant relative change. Relative change equals 5% each year. It grows by 5% each year. So this is a constant relative change. And this is exponential growth. So those are our two classifications, and it's consistent with the language we used to start with, but now we use the actual definitions of each of these things. So our last example is going to introduce the concept of doubling time. So let's consider this not so uncommon scenario that a video is published on a video hosting website and the video goes viral. So this is going to bring us to the idea of exponential growth, or doubling times, or doubling growth in section 8b. So we're asked to suppose a funny cat compilation video has one view upon its immediate publication. So the instant that it's published, one person watches it, presumably maybe the person who made it. Then it goes viral, doubling its number of views for each subsequent day. So in other words, on day 1 it has 2 views, day 2 4 views, 3 days later 8 views, and so on. So we can kind of see the pattern that's happening there. So question A says, how many views will it have 1 week after publication? So, well, we don't have this in terms of weeks yet, so just remember that 1 week is equal to 7 days. And that'll help us along the way. So let's make a table. That might be the first way to see this. It's not ultimately going to be the way that we handle these problems, but it's going to motivate us to come up with the formula that we're going to see in section 8b. So the number of days since publication and the number of views. So 1 day, or maybe even let's start with 0. So the instant it's published, to 1 day later, to 2 days, to 3, 4, up through 7, because that's what that question's asking us. And on day 0, when it was immediately published, it had 1 view. On day 1, the 1 day after it was published, there were 2 views. And then on 2 days later, 4 views. 3 days later, there were 8 views. 4 days later, there were 16 views, right? What we see happening is 1 to 2 is 2 times 1. And then to go from 2 to 4, we multiply 2 by 2. And then multiply 4 by 2. And multiply 8 by 2. And multiply 16 by 2 to get 32, multiply 32 by 2 to get 64, and multiply 64 by 2 to get 128. So we'll have 128 views. Okay, this is a reasonable way to answer the question, given the nature of this question. It's a little bit straightforward. It just doubles each time. It's kind of an easy table to put together. However, on the other hand, we're asked, how many views will there be 30 days later? Do we really want to carry this table out to 30 days? Not really. Okay, we don't really have the room for it anyway. So there's a better way to do this. The thing that we need to notice, and this is actually part C's question, is that we can put a formula together which will calculate the number of views based on T, the number of days since the video was published. So let's just go back and have a look at our table, and this will inform us how to build such a formula. So the pattern we need to see is we have 1, and that came from 0, and then we've got 2, and that came from 1, and then 4 came from 2 down the line. 4 came from 2. How are these values related to each other? Well, this is actually 2 to the power of 0. 2 to the power of 0 is 1. 2 to the power of 1. 4 is equal to 2 to the power of 2. 8 is 2 to the power of 3. 16 is 2 to the 4th. 32 is 2 to the 5th. And I think we see what's happening. So for the number of days, that occurs up here, right? It matches this value, and here, and here. So it looks like you just take 2 and raise it to the power of the number of days that have gone by to get the number of views, and that's exactly it. So let's write that formula down out here at the bottom. We've got the number of views, we'll call it V. V is equal to 2 to the t, and let's just say t is the number of days. Number of days, 2 to the t. So there's a nice formula for us to use. Now when we want to know what happens 30 days later, the number of views when t equals 30, or 30 days later, is 2 to the 30th. We just plug in t right here. T equals 30. And that's actually equal to quite a bit, actually. It's it's approximately, because I've chopped off a little bit, 1.0737 times 10 to the 9th. So that's 1.0737 billion views. That's one way to think about it, or we could write it as that many. Either one of these is fine. They don't specify in the problem, so there is some flexibility. So that would be it. That's the number of views. Not much later, it's about 1/7 of the world's population would have seen that. It's not unbelievable if that's a pretty funny video. Okay, well, practice these problems. We'll meet again in 8B when we discuss doubling time more formally.